Hello, and welcome to this tutorial on creating and using INCISOR Particle Systems. In this tutorial, we will cover the following topics: what a particle system is, how to create a particle system, and how to use a particle system in your project. A particle system is a special type of graphic object that allows us to control the behavior of many separate graphics called particles. Suppose we want to create a snow effect in our application. One approach would be to create a unique graphic object for each snowflake and control the motion of each graphic object manually. While this can work, the computation required does not scale well to hundreds or thousands of snowflake particles. To solve this, a particle system merges all the particles into a single graphic object and uses the GPU to make each particle obey a randomized variation of the same basic particle behavior. To define this particle behavior, we use a particle system definition. To get started, click the Create New button in the Particle System panel. In the pop-up, we'll choose Fountain as the template for our new definition and give it whatever name we like. To see the results of changing this definition, we first need to add a particle system instance that uses this definition. Right-click in the live view and add particle system. In the Particle System panel, we'll switch the definition this particle system uses to the new definition that we created. Now that we've got a particle system up and running, let's look at the Particle System panel to see how we can control the particle behavior. In the Particles section, we have a list of particle types that this system will use. This system currently uses the Sample Particle 2 graphic asset for all the particles. Let's add another particle type and select Sample Particle. Now we see two different particle graphics in our system. We can control the emission rate of each type of particle independently using the particles per second value. This controls how many of each graphic we want to see, as shown here when we change the particles per second of particle number 2. Because two graphics in the same particle system might have mismatched scales, we can also control the scale of each particle using the scale value. For example, if we decide that the circular particles here are too large relative to the star particle, we can lower the scale of just sample particle. Next, we have the emission section. Particle lifetime controls the amount of time a particle lives after it is emitted. Here we have our first example of randomness. If we set the particle lifetime value to 1 and randomness to 0, each particle will live for exactly 1 second. If we increase the randomness value, we increase the amount each particle's lifetime is allowed to deviate from the base value. Note that this random deviation is plus or minus the randomness amount. In other words, the lowest lifetime allowed with this setup is 1 minus 0.9 or 0.1 seconds. The largest possible lifetime would be 1 plus 0.9 or 1.9 seconds. Each emitted particle will then pick a random number in this range for its unique lifetime. Next, we have emission time randomness. To easily observe the effect of this value, let's lower the particles per second of this system. With an emission time randomness of 0, we can see that the particle system will emit particles at equally spaced intervals. By increasing the emission time randomness, we cause each particle's emission time to be delayed by a random amount of time between 0 and this amount. Let's set this back to 0 and bring the particles per second back up. The emission duration controls the amount of time over which particles are emitted. Let's look at the particle system section in the Object Inspector for a clear picture of what's happening here. Here we see the interface for the particle system's playback controller. An emission duration of 0 indicates that the particle system will emit particles endlessly. But if we change the emission duration to 1 second, we see that after 1 second, no more particles are emitted and the existing particles are allowed to complete their lifetime. Note that the playback controller automatically adjusts the end time of the particle system to be the last possible time at which a particle might die. Next, we have emission velocity. This is our first example of a parameter that can be one of 3 types. Currently, the type of emission velocity is set to constant. This means that the path each particle takes will be calculated using an unchangeable initial velocity that, in this case, shoots it straight up at a velocity of 1,000 units per second. If we want to shoot the particles up and to the right, we can simply edit the x component of the velocity to shoot them 1,000 units per second to the right as well. Now suppose we want this emission velocity to change over time. This brings us to an important concept regarding particle system definitions. While it is technically possible to modify the X component of the definition's emission velocity every frame, this is not recommended for several reasons. First, as we can see here, if we slide the X component around in the interface, the path of every particle is recomputed as if that new value had been the emission velocity for the entirety of the particle system's existence, which is typically not the desired effect. More importantly, changing this value causes a costly rebuild of the entire definition, including rebuilding geometry and rebuilding the effect node definition. This is why the changing of the definition in this way is only recommended at initialization. The much better way of modifying the emissions velocity value is to use one of the other two parameter types. If we click the Type button, we can see that this can be changed to an expression or a ramp. First, we'll look at the ramp type. This is a built-in type that allows us to specify parameter values that change over time. If we want each particle to evaluate this ramp using the time at which it was emitted, we can choose an input type of emission time. All ramp inputs are done in a normalized range from 0 to 1. By specifying an input maximum of 4, we indicate that we want the ramp to be evaluated over 4 seconds of emission time. Note that it is common to set this input maximum to match the emission duration of the particle system. But with an emission duration of 0, meaning emitting forever, there is no length of time to match, so one must be chosen here. The ramp initializes with a single keyframe, seen here at time 0. Let's add another keyframe by pressing the plus button on the top right. Now we have another keyframe that has been added at time 1. Because we have selected an input type of emission time, the second keyframe corresponds to the value that will be calculated at our input maximum of 4 seconds. Now we can change the emission velocity over 4 seconds by modifying the values at these keyframes. Let's select the first keyframe and set its value in the X graph to -1000, and set its value in the Y graph to 1000. This will emit particles up and to the left. Then we can select the second keyframe and set its value in the X graph to +1000 and set its Y value to +1000. Then we can observe in the particle system that the emission direction has interpolated between these two values over 4 seconds. We can also modify the ramp's interpolation type to change the shape of the curve between the keyframes. To better demonstrate the different types, let's add a few more keyframes. We'll hit the plus button 2 times to get a total of 4 keyframes. Then we'll set the second keyframe to time 0.25 and a value of 1000. Let's set the third keyframe to a time of 0.5 and a value of 1000, and the last keyframe we'll set to a time of 0.75 and a value of -1000. Notice how with linear interpolation selected, the curve is made of straight lines between each keyframe. With smooth step mode, we get S-shaped curves that ease into and out of each keyframe value. With Catmull ROM mode, the curve becomes rounded between the middle 2 keyframes. The other option to change the emission velocity over time is to use an expression. When we change the type to expression, we see the value is populated with a default expression specifying a vector with no velocity. We can easily restore our original velocity by giving the particles an upward velocity here. We can then modify this expression using some built-in functionality. Using the built-in rotate 2D function, we can change the vector's direction based on the time at which the particle was emitted, similar to the way we did with a ramp. In this case, we can make the emission rotate indefinitely with this simple expression. To best observe emission velocity randomness, let's put the emission velocity back to a constant upward emission. Let's also set the particle lifetime randomness to 0. This definition currently has a constant randomness of 0.3. If we reduce this to 0, we see that the particles all reach around the same height because their velocities all have the same magnitude. As we increase the randomness, we observe an important property of the randomness system. For parameters that are vectors, meaning they have more than one component, the randomness value causes deviation of the magnitude or length of the vector. Importantly, the direction of the vector is unaffected. We can see this as we increase the emission velocity randomness. Notice how the emission directions did not change, but the magnitude of their emission vector is allowed to deviate. To achieve this, the base vector is multiplied by a number randomly chosen from within a range. The lower end of this range is 1 minus the randomness value. The upper end of this range is 1 plus the randomness value. In this example, this works out to scaling the vector by a number randomly chosen in the range of 0.7 to 1.3. The emission cone angle controls how much the emission velocity vector is allowed to be randomly rotated away from the base value. Notice how a value of 0 emits particles in a straight line, while raising this all the way to 360 emits particles equally in every direction. Emitter position allows us to animate the position from which particles are emitted. Notice how grabbing the particle system in the GUI and moving it also moves any previously emitted particles, which is often undesirable. Using the emitter position parameter, we can animate this position without affecting the behavior of particles that have already been emitted. Let's reduce the emission velocity to make this more visible. If we then use this expression, we get a moving emitter position that does not affect the previously emitted particles. The emitter shape lets us choose from a few predefined shapes where particles may be emitted. To make this more apparent, let's lower the particle lifetime to something very short and increase the particles per second to something very high. We can now see that by choosing the rectangle emitter shape and giving it some larger dimensions, we get particles emitted from a rectangle. If we switch to circle uniform, we see that we get particles emitted uniformly across a circle. If we choose circle center, we get a similar circle, but with particles more likely to be emitted near the center. Choosing custom lets us populate the custom emitter shape code, where the expression is responsible for choosing a new position for every particle. For example, we can emit particles only along the edge of a circle using this expression. A few random number variables are already available to use in expressions. These are named ran0 through ran5 and each have an x, y, z, and w component. Here we have used ran1.w. Each of the provided random numbers is in the range -1 to 1 and is unique to each particle. The system automatically recycles old particles after their lifetime is over so that it can create fewer particles and use less memory and setup time. The particle pool count number reflects how many particles were actually needed to support the requested emission parameters. It is often far fewer than the number of particles that appear. In the physics section, we have the force parameter. This is often used to simulate gravity. Notice how the particles move down more quickly as we increase the strength. Extra velocity x and extra velocity y are an additional factor that is added to the motion of each particle and are often used to simulate things like wind. Notice how all particles are pushed to the right as we increase the extra velocity x. Motion stretch will scale each particle along the direction it is moving. Combined with the motion stretch alpha influence, this is often used as a quick approximation of motion blur. To see this, let's lower the sizes of the particles and increase both of these values to 0.2. The age ramp expression lets us modify a particle's age value. For example, we can make a particle move through the beginning of its lifetime more slowly, then speed up by squaring the age. In the rotation section, we can control the rotation speed of the particles. This system currently has a rotation speed base value of 0, with a randomness of 180. This gives us a system where some particles will arrive at a rotation number near the middle of the range, resulting in very little rotation. Suppose we instead want each particle to spin quickly in either the positive or negative direction. To achieve this, we can remove the randomization and use an expression for the base value. We'll use the x component of rand2 to get a random number that is unique to each particle. Because these numbers are in the range -1 to 1, we check if the number is negative or positive to choose which direction this particle should rotate. Let's now put this back to 0 rotation speed. The initial rotation sets the rotation of the particle before any rotation speed or any of the additional rotation parameters are applied. If we remove the randomization of the initial rotation, we see that all particles have the same rotation. The rotation sway strength, rotation sway speed, and rotation sway phase all work together to sway the rotation back and forth. Let's increase the particle lifetime so we can see this effect more clearly. If we set the speed to 1 and the strength to 100, we see that each particle rotates back and forth over its lifetime. Because the rotation sway can cause particle rotations to sync up, which can be undesirable, The rotation sway phase is available to offset the rotation sway of each particle. The wiggle section lets us control an extra movement factor on each particle. Let's remove the other motion on these particles to make this more obvious and set the emission shape to a rectangle. Now we see that each particle remains in its initial position. If we modify the wiggle parameters, we can see that the wiggle strength and wiggle speed work together to move each particle in a back and forth motion. If we make the X and Y speeds mismatched, we can get a more chaotic feeling wiggle motion. The last wiggle parameter is best demonstrated if we set the emission shape to a point, lower the sizes, and increase the particles per second. By doing this, we can see that the sine wave nature of the movement means the particles will naturally fill out a rectangle, since the X and Y are wiggling independently. We can alter this by using the wiggle circular strength. Setting it to 1 forces this movement to fill out a circle instead. Moving this value outside the 0 to 1 range can also create some interesting effects, as we see here. The particle scale lets us control the scale of each particle. Let's set this to an expression that makes each particle scale up, then scale down over the course of its life. First, let's use the smooth step function to scale the particle up. The age ratio variable represents how far through its lifetime this particle is, expressed in the range 0 to 1. We can then modify this further to scale the particle down again using another smooth step function. In the color/alpha section, we can control the color and transparency of the particles. First, let's change the color of all these particles by lowering the blue channel of the color. Then, let's hue shift each particle using the particle hue shift parameter. Changing the base value will change all particles together, but note how the randomness parameter can give us a useful variation in the hue of each particle. We can also change the alpha value to change the transparency of each particle. Here, let's use a ramp and tell it to use the age ratio as the input. This means the lifetime of the particle will be mapped to the ramp values, with 0 being the moment the particle is emitted and 1 being the time it dies. Let's set the first keyframe's alpha value to 1. We see that the particle's alpha starts at 1 and fades to 0 over the course of its lifetime. In the randomness section, we can control whether the default behavior for any particle system using this definition will change the random seed of the particle system every time playback is started. This can be very useful for making the random variations of each particle be different every time the particle system playback is started, so that it appears less repetitive. The seed can also be specified manually in the random seed field. The particle seed draw order can be used to randomly shuffle the interleaving of particles. This is only meaningful when a system contains multiple graphics. Because changing this value causes a costly rebuild of the particle system's geometry, it is recommended to only set this value at initialization. The randomness distribution is an advanced setting that can bias all random numbers towards 0, which can alleviate certain visual artifacts, but is not typically needed. Now that we've gone through the entire panel, let's see how we use a particle system in code. Earlier, we added a particle system to our scene by right-clicking in the live view. To do this in code, we'll call nc.addParticleSystem. We'll pass it the definition we created earlier, which can be found in NC Particle System defs, and tell the particles to play using its playback controller. Now that we've got our infinitely emitting particles created, we might decide dynamically in code that it's time for these particles to stop emitting. To gracefully accomplish this, the particle system has a stop emitting function that stops the creation of new particles after the function call is performed, but allows existing particles to complete their lifetime. To see this, let's add a keystroke callback where we call this function. If we do nothing, these particles will never stop emitting. But once we press a key, we see that the particles have stopped emitting, but the existing particles are unaffected. A noteworthy property of INCISOR's particle systems is that we can set the playback controller to arbitrary time with no performance cost. Jumping to a different time does not require stepping through the intermediate particle states. Because of this, we can even tell the playback controller to play the system backwards with exactly the same performance. This concludes the INCISOR Particle System tutorial. Check the link in the description for more tutorials, and feel free to leave questions and feedback on our Stack Overflow and subreddit. Enjoy creating with INCISOR.